Hello and welcome. In this video, I'll be talking about alignment of sequences, how the algorithms that we use to get the alignments. There are two main types, global alignment and local alignment. Global alignment is the standard kind of what you would think of when you're aligning two sequences with each other. Usually your a priori assumption is that the sequences are already quite related to each other and you're trying the global best way to fit them together with as many matches as possible. Local alignment uh, allows you to look at regions of sequences that align well with each other while at the same time ignoring perhaps large regions of those sequences that don't align with each other. We also have two things, pairwise sequence alignment. So this is the alignment between two sequences, but we also have multiple sequence alignment. And this is when you have multiple sequences that you're trying to align them all with each other. The top here, we have an example of a local alignment, and you can see that we have a smaller sequence here, which is aligned with part of a larger sequence, and we've completely ignored what's going on in the ends here. But quite good agreement, many matches in the region that is aligned. In contrast, we have global alignment, and here we've tried to spread out the alignment so that the sequences are aligned throughout. So there are no regions in the sense that there are in local alignment, no domains. Here, both sequences are kind of assumed to be the same size, that they should be the same size. Local alignment is good for things like when you have maybe different genes, sequences that are different from each other, but that have conserved domains. But these domains might be offset, their position might be shifting due to the variable lengths of regions in between. And you would want to align in such a way that you get these local domains to align with each other while potentially ignoring these other parts. The first of these kind of algorithms that came about was the Needleman-Wunsch algorithm from 1970. And this was building off of an idea from the 50s called dynamic programming. And this was the idea that certain problems could be solved by breaking them recursively over and over and over again into simpler subproblems. So for sequence alignment, this is very important, right? Because alignments of, we already said this, that two amino acid sequences, if they're 100 amino acids long, you have like 10 to the 75 different alignments that are possible. So it's not feasible to do a brute force, just check every single alignment, rank them, and then pick the best one. So instead, these dynamic programming algorithms divide the problem into smaller local problems, but then still manage to find the highest score, the best alignments, using this approach much more efficient. And the basic, the kind of core computation, this subproblem that's taking place in the case of Needleman-Wunsch is the computation of one element of a matrix. So this matrix will we would have rows corresponding to the residues in one sequence and columns corresponding to the residues in the other sequence. And each cell or element in this matrix would be computed according to this particular algorithm. And the way it would work is you have three candidates for what could go into this cell. And the candidates come from either introducing a gap, adding a gap penalty to whatever score is on the left of the cell that you're looking at. Also, a candidate comes from adding a gap score or a gap penalty to whatever cell is directly above the cell you're looking at. And then the third option, which is taking the substitution score for the particular residue pair that you happen to be looking at for for your row and column, and then adding that to whatever is diagonally adjacent to the cell that you're looking at. And then this procedure would be repeated over and over again to populate the values in the matrix. So here's an example. So if we have these two sequences, this line and this sequence here is aligned, and we want to find the best global alignment for these two sequences with a gap penalty of -8. In this case, we just use the simple linear gap penalty. And then we have here a substitution matrix with our scores. And the first thing we do is we add these gap rows here, a gap column and a gap row, and the top leftmost corner gets a 0 as our starting point. And so again, here is this algorithm that we're going to follow. For each of the cells, we have 3 candidates. One is going to add the gap score to whatever's above. One is going to add the gap score to whatever's to the left. And one is going to add the substitution score from this matrix to whatever is diagonally adjacent. And then we'll take the best of these 3 possible candidates as our value for each respective cell. So actually, the first step, though, is to fill in these rows with gaps, gap penalties. So this first row, and this corresponds to just frame shifting the whole sequence. So if we were to start the alignment here and start looking at the eye here paired with this eye, for example, then we would have to begin by already adding several gap penalties. So that's what we're doing here, is just adding cumulative gaps. But then we're ready to compute the value of the first element in this upper left here, because we'll have now places to take our 3 candidates. So we can add our gap score to the left, -8 here, to get a -16 as one candidate, -8 plus this -8 on the top here to get another -16. So these are the 2 gap candidates if we were adding a gap at this particular alignment position. And then the third candidate, which is adding the substitution score for, in this case, I with T. So we would look that up, I and T. We see that it's a -1 here in the matrix. So we add -1 to 0. And then we have these 3 candidates, -1, -16, -16. And -1 is the best of these 3 possible candidates. So that ends up becoming the value for this matrix element. And in doing so, we accept then this direction, the diagonal direction, as the arrow that leads to this cell. And so when we would move on, we would just drop out the arrows coming from the other 2 rejected candidates. And then we just continue this process for every single cell in the matrix. So the next one here, -16 plus -8 is -24. So that's the horizontal gap candidate. -1 plus -8 is -9. That's for the vertical gap candidate. And then S substituted with T here. We look it up. S for T is a +1, score of +1. So we would add +1 then to the -8 to get -7 as the third candidate, the diagonal candidate here. And of these possibilities, -9, -24, and -7, -7 is still the highest number. So we would accept that then as the value for this cell, and the diagonal direction again here as the winning direction. In contrast, you can see in this cell, the horizontal direction ended up being the winner, the winning score being -9. So in that case, in this particular cell, it was better, more optimal to introduce a gap than to accept, for instance, the pairing between I and H, which presumably has a bad score, or at least not good enough to make up for the fact that we had introduced a gap in the first step here, going along that path. And so you can see it's generating several different kind of pathways, but all of them are sort of optimal given their current situation. So if your current situation is you introduced a bunch of gaps in the beginning and you happen to be here, you're always looking for a way to try and improve your situation, whether it's by introducing a gap in the vertical direction here, or accepting a substitution event in the diagonal direction here, always at any point in time trying to optimize in the local environment in this matrix. And then you just populate the entire matrix like this, fill in all the appropriate arrows and the scores, and at the very end you're left with a score in the bottom right hand corner here. And oh yes, and one note is, so occasionally you will get a tie. So both directions here led to a score of -17. So you would take 2 arrows going in to that particular cell. And then what we would do is execute something called the traceback. And this is where we would start from the end and follow the arrows, the ingoing arrows, all the way back to the origin. And as we do so, we would keep track of the alignments at each position. So we're at the end here, we're starting with D paired with E, but then we introduced a vertical gap here. So in fact, what we really want is E paired with E then, which makes more sense. And you can see why the gap was introduced, because E paired with E is better than E paired with D. And then we have N paired with N here as well, and so forth, G paired with I. And if you do this, you can produce the transcript for your alignment. You can see this is the final product. And it's not so good, you'll notice. And this is where playing around with the gap penalty can make a huge difference. So in this case, our gap penalty was -8. But if the gap penalty is relaxed to -4, we get a very different result. So you can see now more matches are occurring and also more gaps are being introduced. There's also another trick, which is to populate the first column and row with zeros instead of n gaps. And this has the result of not penalizing for n gaps. And in certain situations, this can be advantageous. So to conclude, in Needleman-Wunsch, you construct a matrix with scores. You fill in, you start with n gap scores, either using the fixed gap penalty as we did, or using the forgiving n gaps, setting them to 0 strategy that we did. You can then compute the alignment scores from boxes with these 3 corner forming candidates, and then always accept the highest scores and directions so that each box has a winner. You iterate this process until the matrix is full, and then perform the traceback. And while you're doing that, you fill out the transcript. So then there's the Smith-Waterman local alignment algorithm. And this is actually really similar to global alignment. So you don't have to learn so much new stuff, fortunately for this. And this is from 1981. It's another form of dynamic programming. And as we mentioned, the motivation for this was for finding domains. And the way it works is it's very much similar. So you have the same system of generating candidates from the corners, from the left and from the top. But the difference in the case of Smith-Waterman is that anytime the score that you produce is negative, you would simply set it to 0 instead of accumulating larger and larger negative numbers. You always set it to 0 each time it goes below 0. And this has the result of making the algorithm forgiving of cumulative gaps. So like you don't see these huge accrual of large gap penalties in the beginning. And this is because of the effect of the local alignment, right? We're enabling the sequences to ignore, say, large sections of sequences that don't align with each other and just find the optimal regions. And the other thing is, in this algorithm, rather than starting from the very end for our final score, what we'll do is start from the maximum, the point of the highest score. And this has the result of, maybe we'll omit the end if it doesn't align well, as is the case here. So you can see that the D was dropped because we determined that the best alignment really started from E and N here. So that is local alignment, and you can see just a comparison here of the matrices that maybe you generate for different gap penalties. And that is all I'm going to say then about these alignment algorithms. So I'll see you in the next video.